So in talking with Elaine and Raquel, the idea today was to talk about some notions of high-performance computing for data-intensive science. And so I've tried to do a little bit. There's good news and bad news. I have too much. That's the bad news. The good news is, actually, not knowing the audience, I over-prepared, and I think a lot of this is old hat, and I'll go through it quickly. Starting with the acknowledgements that not much of this work is mine, but I'm rather here representing and presenting stuff on behalf of my collaborators, my organization, people I've worked with in previous projects, and all supported by mostly NSF, although I work at a DOE lab, and I should also thank the Department of Energy for hiring me. I'm speaking mostly from a lot of my experience recently with the DataONE community, and this is a large NSF project. There's an early picture of some of us there at an all-hands meeting in New Mexico. It's chaired by Bill Michener out of the University of New Mexico with a lot of collaborating institutions. And just an outline of where I would like to try to go today. You won't see this outline again, but it's an attempt to try to weave a story of data leading to science with the opportunity for high-performance computing, what that enables, and what problems it either creates or leaves unresolved. So data gives birth to science. I thought this might be a controversial topic, but at lunch, the opposite was asked, which was, is e-science anything but data? So that's great to be here with this community. There's some folks I talk to where the idea is it's all computing. I have a hammer and you're a nail, so how can we compute faster? But in fact, the history of science from the Renaissance is sort of a rejection of Plato's allegory of the cave, that empiricism matters and empiricism depends on data. We learned that with the revolutions in astronomy. I did that for you, Richard, knowing that we needed an astronomy. I didn't know we'd have other astronomers here. But also in the medical community, I mean, the discovery and the utilization of the microscope is a prime example here. And so, in fact, the workflow of this science is the data lifecycle. This is probably not a surprise to most in this audience. To some others it is. They think of workflows as specific tools that can be automated like Beeple or Kepler or Taverna or Galaxy. But in fact, if science comes from data, then the workflow of science is the data lifecycle, the entire data lifecycle. And this is the particular incarnation that we tend to use in DataONE after much debate. I know it's not a universal one. An interesting notion here is that, in fact, different people care differently about different aspects of the data lifecycle. So, in fact, if you look about collaboration in science, where most science today is done collaboratively, different team members have different sort of care about, so stakeholders and care about analysis. And this is a representation of a particular survey we did within DataONE, where the size of the particular bubble indicates their level of interest. So different people care about different parts of the life cycle. Some of you may know Carol Tenneper and Susie Allard and their colleague Kimberly Douglas. They wrote an article a couple of years ago talking about data sharing practices among scientists. So a self-selected group of 1,300, mostly academic, and trying to do a baseline assessment of where we stand for utilizing data management in the conduct of science. And there was good news, right? People are interested in sharing their data. They would share their own data, 81% to some level of sharing, and even willing to place it in a repository 41% of the time. This was a couple of years ago. I think it's probably even changed beyond that. There's a lot of stuff in that particular PLOS1 paper, but the two that I'm bringing out is one, a willingness to share, but the other one, when asking what are your mechanisms for sharing, it's less positive, right? Some people use FGDC or EML, different metadata description languages, and a common answer is, what's that? And so I think the point is that, sorry, okay. The answer is that there is a desire, but there is currently a difficulty in putting that into practice. So I think that's where we can make a difference. Now let me move on and talk about big data. This is all the rage. If you're not doing big data, you're not surfing the big waves these days. And so it begs the question of what is big data? And you find a lot of different answers. I certainly have my own opinions, and we'll share them. I put it, as an example here, again, the virtual observatories. I didn't know we'd actually have people actively engaged in that in the audience, so that's great. But in things like high energy physics experiments where your level 3 triggers generate huge data sets and you're sifting through enormous amounts of data. But in fact, you could ask this question of what is big data? Is it just huge data? Is it huge for my discipline, right? So I may have a huge archive for my particular area of work, but it may be small compared to other disciplines. Or is it just huge because it's straining me, right? If I could handle it with those USB drives that Richard mentions and a lot of professionals mention, it's just irk you. But in fact, if you get too large for those, is that the definition of big data? And I think I definitely come down to the last two. That is, does it strain the resources that I have to manage data? And is it larger than I did, last year or last decade or last week? And by large, I mean by orders of magnitude, base 2 or base 10 or something. But that begs another question, and that is, what is the measure of large data? What's the metric for it? And in the circles that I run in, people often say, well, it's how many petabytes you have, or how many gigabytes a second of I/O do you need to access the data, or these sorts of questions. And in fact, I think that's part, but not all of the answer. So I have sort of kind of a Maslow's hierarchy of needs pyramid. And when you live in the data center, right, I don't want to say you're lower, but you are lower on the pyramid, right? In the same sense with Maslow's hierarchy, you need to solve the bottom parts first before you can even talk about the upper parts. But it's only when you get to the top that you've actually accomplished your mission, which is to enable science. So if I'm speaking to you about, racks of petabytes of storage, I'm layers 1 and 2. And if I'm in, the library world or the information science world, I'm often talking about things like semantic integration or data harmonization. And in fact, all of those are prerequisites for success. But we do have different cultures. But it's not a bifurcated culture. I see this kind of a continuum. And so in fact, I think as we tend to move forward, you'll find that a lot of the things that stress the lower levels turn out to be grand challenge information problems. So for instance, the data harmonization problem may be one of the largest computational problems that we'll deal with in the future. And in fact, there's a company that's made money out of those sorts of things. It's called Google, right? And we don't mention Google in supercomputer centers, but if you aggregated it, it is quite a substantial physical infrastructure. So where are the opportunities? Well, the opportunities with big data are where the big data is, but there's different types of big data. So for DataONE, we're looking at areas like biological, ecological, environmental areas. We can't be everything to all people. We don't have the resources for that, so we've tried to focus in a disciplined fashion to have some coherency. Right, we very often have a data reuse use case for civil engineering, phylogenetic analysis, and high energy physics. Right, those guys just tend not to reuse each other's data very much. So we're trying to look at areas where you would have data that would be reused. So for instance, you may have remote sensing satellites that's gathering spectral information about ground cover, temperature, those sorts of things. But then you can model it also with land surveys. So if I have single kilometer pixels on my satellites, if I can survey a kilometer and measure trees and tree radius and leaf cover, then I can begin to correlate and then extrapolate to other areas. And so that's kind of what we indicate here, is that you're stressing big data up and down these sorts of observational, remote sensing projects, citizen science, or public participation projects. And you want to figure out a way to sort of begin to knit them together. Let me turn and talk about HPC at this point. So having framed the big data question, you might ask, why do we care about big computing? Well, we might care about a big data center, and that's a separate issue. But at computing, you have sort of different sorts of scales. And we have fun with that at Oak Ridge. I think San Diego has fun with that. We have half dozen places around the US, a couple dozen around the world. But it's a big effort. So at Oak Ridge, we have the Oak Ridge Leadership Computing Facility. And in fact, we have, on the first floor, we have 3 large machines in play right now. in the back, you see several rows of racks of Jaguar, now Titan, which was the largest machine in the world when it was commissioned. Titan is now the largest machine in the world for DOE. You have the Kraken machine that's actually operated by the University of Tennessee, but it's on the same floor. And for a long time, it was NSF's largest machine. It's no longer the case there. There are Stampede and Blue Waters now in existence. And you also have Gaia, which is NOAA's largest machine, all in one basketball court for the Final Four fans. The scale is fairly large, right? You have 2 basketball courts. There's another floor right above this one. The facility itself has tens of megawatts of power that you have to bring in. In fact, the unique advantage is maybe, the availability of hydropower and nuclear power in Tennessee makes this very, very possible. You have issues of bringing in power. If you ever go visit, you'll find that we're in the back of the room, and the reason is because they chose not to bring the bus bars forward in the room and save $1 million. So, the view is not great because it's across the room, but it saved money. That's the scale of things. But also the machines themselves have quite a bit of scale. So the current machine that's on the floor is Titan. Again, the same footprint as Jaguar. 27 petaflops currently peak, 700 terabytes of memory. It's interesting to note that actually the CPU in it is Kepler. We used to joke that the computers that designed our nuclear weapons had their architecture dictated by the gaming desires of 14-year-old boys. And that was literally true. But today we're moving forward, and what we're finding is the world's largest computers have their architecture dictated by what people want in their next smartphone. By the way, if you go to Kepler's website, or just search for NVIDIA and Titan, they co-branded their marketing back with NVIDIA. So they give this, looks like a game, zeroing in targeting Oak Ridge, and then you can buy Titan and actually put it on your machine, a single K20 processor, and put it on your desktop or server. So it's very interesting. So what is the opportunity that you provide when you have high-performance computing? Well, as you get larger and larger amounts of data, you get the ability to examine the outliers. I call this, we have the ability to breed flocks of black swan. So if it's just one unusual event, you look at it and you examine it, and it's an anecdote. But if I can have a statistically significant sample in the 3 to 5 sigma range, now I have something to look at. Can I talk about 500-year floods and understand whether the notion of 500-year floods is changing over time in a secular fashion, or are we simply seeing a statistical sampling? If I'm looking for the best of something, right? Second place is first loser. And so you're looking far out into the tail to find the very best thing you can find. In short, the economists would call this if you have a very non-uniform utility function. And so the opportunity is to take ever larger sets of data and apply ever larger analysis workflows and discover new information that hadn't been seen before. Or, as I call it, the Nate Silvering of America. So before Nate was so popular, this is actually a couple of years ago, was a Pathfinder project we did with DataONE, where the folks at the eBird project in Cornell had 300,000 observations, volunteer observations. I could never write a proposal to get that sort of effort, but they get it for free because people like the birds. And it had information all across the U.S. on bird presence and absence, but it wasn't complete. And they turned around and took about 10 to 15 different variables that they could get from remote mapping satellites, from land cover databases, and integrated that into a geographically specific land cover model, geographically specific clustering model, so then they could predict down to much finer scales the presence or absence of particular species. And this actually ended up being used in the, both Secretary Salazar, as Interior and Commerce, both presented this in a joint news conference. It's used as basis now for federal land management. If you're in a particular Army base, maybe, that's on a flyway, you might want to not do certain things during the flying season or during the breeding season. And so, in fact, you have actionable scientific results that were previously impossible. And these folks in this project were computing orders of magnitude more than they had used before. And I had helped them when we were working with TerraGrid The ironic part was on the TerraGrid project, this was seen as a starter project because it was so small. So it sort of demonstrates the notion of big. What is big? Big is bigger than what you're used to. And it brings to mind something that I love to do. I like to be Santa Claus, where you come to people and you say, what would you do if you had an infinite amount of computing? And you get, you can't do that, blah, blah, blah. There's a reason it's not. You'll heat stuff up. We can't afford it, blah, 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 blah. Say, fine, right? But you keep pestering it. In about 6 months, you'll be sitting down to lunch with these people, and they'll say, I could run 10 cases. In those 10 cases, I could examine 10 more things. And the light goes off. And then suddenly they're doing stuff that they believed was impossible before. And now it's under the belt. That's a breakthrough. So where are the bottlenecks, right? This is a great story, right? But it never stays that way. Well, the bottlenecks are three sort of classic things, right? I've got to manage the data. If I've got more data, I need to do more management. I've got to manage my metadata. I've got to preserve my data. That's harder the larger the data is. And I have a lot of things that don't scale with Moore's law. Salaries don't go down as Moore's law. My computer is a lot cheaper than it used to be. My computer on my desk used to cost my salary. It's less powerful than this, and I'm not paid as much as my phone costs. So this is a graph. I think, actually, folks will be familiar with this, but this is a paper that Matt Jones did a long time ago now, looking at 2 studies in the same scientific area. And these surveys just chose to create their data reasonably, but incompatible. And so you have to do issues of, is this an area, or is this an area density of species? Do I encode the species as part of the metadata, or do I encode the species as part of the data? And if you want to take surveys and reports from multiple studies, this is where you spend all your time, this human time that doesn't scale with Moore's law. Second problem, what's your metadata standard? Right? This is a graphic that from Indiana University's program with Jim Riley, and I just love it because you look at this graphic and you see all these dots, and you go, all these are different metadata standards. And you magnify them and you see that these are very specific things. So, if I tell you I have my data in repositories and it's using good metadata standards, you're only just starting. And finally, data preservation practice. This is a graphic. It's not quantitative, but Bill Mitchell uses it about, I generate my data, I forget a little bit, maybe I lose my drive. If I'm lucky, I'll keep it till I retire. And then it probably gets lost when I die. We've been asked in DataONE to do decades-long preservation. And we need to change this. And so if we don't change this, in what sense are we talking about science which is reproducible, right? Science comes from data. If we want to do scholarly investigation, we need to be able to do reproducibility. If the data is not available, how can you reproduce? How can you disprove? If you find a discrepancy in your study and my study, was my methodology wrong? Was my data wrong? So we need to preserve the data. We need to publish the data. So one of the answers that we're looking at with the DataONE project is trying to generate an ability to have a collection of data repositories to address some of these problems. Let me see if I can...
How does a scientist use DataONE to preserve research data? Scientists collect data using many different methods. The collected data is often referred to as a dataset. Spreadsheets or data-based software are used to store the collected data and enable analysis or transformation of data. Metadata helps people find, understand, and reuse a dataset. A scientist deposits data by visiting a data repository that participates in DataONE as a member node. The scientist connects to a member node repository using one of several familiar software tools. The scientist uploads the dataset and metadata to her member node repository. The member node repository confirms the dataset and metadata have been successfully deposited into DataONE. DataONE's central services are performed by coordinating nodes. They contact each member node to find out if any new datasets have been deposited. The member node responds that a new dataset has been deposited there. The metadata for a new dataset is copied to one of the coordinating nodes. The dataset's metadata is copied to all DataONE coordinating nodes. Coordinating nodes then ask some of the other DataONE member nodes to get a copy of the scientific data. Member nodes replicate datasets by interacting directly with each other. The source member node sends a copy of the dataset to each DataONE member node that has requested it. Centralized metadata enables searching. Citizens and scientists can access datasets held at a DataONE member node. Member nodes will soon begin collecting statistics on dataset use. Scientists will be able to find out how many times their datasets have been downloaded and reused. DataONE is designed to be a reliable system for sharing and preserving scientific data. The coordinating nodes poll every DataONE member node to verify its health and stability. Scientists who deposit their data in DataONE can refer others to DataONE without having to search their own computers or labs. By citing DataONE in the papers they write, readers can access data directly from DataONE. DataONE: Data, Discovery, Knowledge for a Sustainable Future.
Something that we have is nice within DataONE is that's actually our Assistant Director for Education and Outreach, so it's not a professional voiceover. We have that in-house, and it's often much nicer to hear Amber Budden say that than me. She does it so much better. But that's the general notion of DataONE, is we're trying to create an interoperability service layer on top of different archives, which we call member nodes, with a replicated global metadata catalog. And again, within related data fields, or related scientific fields rather, so that you can begin to reuse the data and reshape the data, much according to like the eBird exemplar. And so we're creating an ecosystem, an interdependent ecosystem of scientists, of member nodes or archives, of people who care enough to fund this, the resource providers, and also receive the results out of it. They have skin in the game, as well as DataONE itself as a infrastructure creator. We have currently 13 member nodes, different types of member nodes, new ones coming on board like Dryad. We mentioned data publication. There's Dryad is participating here. So if you're interested in data deposited at Dryad, certainly you can go straight to Dryad, and that's where they'll probably see most of their users come and use their data. But in addition, if you might be looking through a larger data set, you might end up accessing Dryad data through a larger collective. We have over 300,000 data objects currently. Our growth curve is steep, so check in later. In addition, on the life cycle, not only do we provide these tools, but we provide tools for scientists who want to use and reuse data. And we have object identifiers, which are persistent, like DOIs, not just DOIs, right? We're multiple sets of data archives, so we try to meet our member nodes where they are. If you use the DOI, it's great. If you use an easy ID, that's great. If you want to use some other persistent identifier, we try to accommodate. And in this way, we enable data publication. So we've mentioned that before today. For identity, it's kind of interesting because, again, we're a collection of member nodes. And so we try to use federated identity solutions, CI login and in common, for example. And in that sense, we hope to help provide for all aspects of the data lifecycle and augment it with DataONE tools and data that's available for discovery and analysis at the collection of member nodes that participate in DataONE. Let me just close with a couple of thoughts, and that is, I know a lot of folks are familiar with the Holdren memo. It's actually in response to a White House petition, but essentially it was a directive asking for science to be made available, scientific results to be made available openly. Some things to note was that actually the Holdren memo dealt specifically with federally generated data generated by federal agencies. And so you could ask the question, well, how is this going to happen? And I think DataONE is very interested in participating in that. And for a couple of years, our nominal slide for this is, community building, right? You build actively engaged communities with participatory governance, and then you create organizational sustainable models. Most of you may realize what these sustainable models represent, right? And at DataONE, we believe that very strongly, that if you look for places for these activities to have a home, particularly in academic institutions, It's the libraries and the museums, right? They have a long-standing notion. They've existed for decades. The data center has not. And that's a specific area that we're looking for outreach. On the other hand, it's not only libraries. We may have institutional repositories. We may have society repositories. We may have agency repositories. NASA does a lot of agency work. But this is what we see as a vision for sustainability for these sorts of activities and where they live. That's why I think DataONE is kind of relevant to what we're talking about today. Let me just end with two plugs. One is, we've heard before and may hear again this afternoon, the DMPTool. I think it's a very good tool. I've been actually working with them for a while and will continue to work with them. And it's also undergoing its next revision. So it's a good time to note deficiencies or opportunities for improvement. If anybody has anything, I'd love to hear about it in the question period or whatever. And finally, the last one is, of course, speaking a lot about DataONE here. Please save the date. We're actually having our users group meeting. I know at least one person in the audience that'll be there. But like I said, it's a participatory design, or as Amber says, participatory. We translate English to English there as well. And that's in July. It's co-located with the ESIP Federation meeting in North Carolina because, again, ecological, environmental, biological work. And thank you. There's also a URL there where I'm trying to upload this to SlideShare. I think I've gone over too much.